that your microphone's doing anything?
Yeah.
You've got to switch it on. But
Just
right, so let us know when we're ready. I was just checking that the microphone is working for you, so I might as well plug a theme issue that appeared about a year ago, which is entitled Reliability and Reproducibility in Computational Science, Implementing Verification, Validation, and Uncertainty Quantification in Silico. And I'm really delighted that Erik, who was a contributor to that, and I invited you to contribute. We've interacted quite heavily over a period of maybe 2 years or so to get to that point. The first time I saw you was about 2 hours ago in here. Very nice for you to be there. Are we confident that the mic is now working?
She was talking about something else, workflows in science, and how to make them computable. And she said in her lecture that we have a reproducibility crisis. And I thought, oh, we have a reproducibility crisis. That's kind of crazy because it's such a cornerstone of science. And I thought, I want to know more about this. Why haven't I heard about it? That was sort of my concern then. And I started looking around and trying to read about it and understand it. And it was really hard. There were lots of papers about it, but they didn't make sense to me. So I decided I have to understand it better. And in my mind, because it's such a central part of the scientific method, why aren't the definitions I read, why aren't they sort of defined based on this method that we have? So I thought, okay, then that is what I'll try to do. But first, I just need to find someone who's thought about this scientific method and made a sort of process view out of it. But I found that it was really hard to find this as well. So I thought, okay, I'll have to give it a shot and make one myself. And I basically put up this figure. So we have the world. We walk around in it, observe it. We build beliefs about it, okay? And some of us, when we observe the world, we build sort of scientific theories and we want to prove them. So we form sort of hypotheses that are genuine in order to falsify our beliefs about the world, proper. And in order to test these hypotheses, we make some experiments. We end up with a research protocol, and then we implement these experiments. We try to run them and do them. So we have this experiment that we conduct. We get an outcome. We analyze this outcome. and then we have to interpret what this analysis tells us. And then finally, if this conclusion that we draw based on our experiment changes what we thought before, we have to update our beliefs. As good scientists, this is what we do. This is the method sort of for discovering knowledge, and we should update our beliefs. So that is the whole process. It ends up with maybe updating our beliefs if we get some results that tells us to do that. And then I thought, okay, let's look at the definitions of reproducibility out there and see how many of these are actually covering all these parts of science that I sort of put into this figure. And so the red box here that tells you tell you that they don't cover this part that I'm talking about. And if you're very interested in this, you can read this paper. I'm just going to say that. So basically, the definitions that we have, they are not really tied to scientific method, and they don't really cover all of it, what I think is important. So as a good scientist, I had to make my own definition of reproducibility. I'm sorry about that. We had actually many enough. So I say that reproducibility is the ability of an independent investigator to draw the same conclusions from an experiment by following the documentation shared by the original investigators. Some important terms here. First, reproducibility should be done by independent investigators. So if I have an experiment, I redo it myself, I only repeat, okay? So someone else should do it. It should be something different there. And of course, in computer science, this means that this difference here, that someone else does this experiment, it's not just pressing the button or running the command on the same computer, same everything, then you don't reproduce. There need to be more difference than just pressing the button of a computer program that someone else wrote. Okay, and then the next term here, it's about the conclusions, okay? So we should draw the same conclusions, which means that I reproduce your result if I don't have to update my belief about the world because I assume you were right. But if I have to update my belief, then I didn't reproduce your result, okay? So that is important. And then it's by following the documentation. So if you do an experiment and you document it and share it with me in form of a paper maybe, then okay, then I can do what you told me to do, and then I should base my experiment on your documentation. And there are, of course, different types of documentation. And you have to remember that I'm coming from this as not only a computer scientist, but I dabble in machine learning and AI. So my view here is informed by machine learning. And I think that these definitions and what I talk about here, they are much broader than that. But the good thing about thinking about machine learning is that you capture everything on the computer. Okay, so and it's important to understand that a reproducibility experiment is very different from the initial experiment done by the original investigators, okay? So they had to go through this whole process of scientific method in order to get to something. But I can just, if I want to reproduce, I just read the documentation. And then I have to add something. And that's what not in the documentation. And then I can do the reproducibility experiment and I'll get a conclusion. And then based on whether it's the same as you had, I might have to update my belief. Okay, so this is then about, so we can think about this reproducibility experiment in different sort of sciences. So first of all, it's psychology. So, and I use psychology because they are not running everything on computers usually. They are working with humans. So I'm only working with computers. So they have a text that documents the study protocol, and they have an evaluation protocol that is also text, that is written by the original, investigators of this problem. And then I, as a psychologist now, I need my own laboratory, I need my own subjects, and then I do what they wrote in their protocol as text, and I do that to my subjects, and I get an outcome. And then I can do the same analysis and interpretation as they did, based on their written protocols or evaluation protocol. But I have to add quite a lot of myself when doing this reproducibility experiment. And compare this with machine learning here. So in machine learning, you can documentation means much different things. It's not only text, okay? So I can have the study protocol even as code. So I'll have a part that is text, of course, but I can have most of it as code. And I have digitized data. I have the machine learning algorithm that I want to test and understand more about. I have it as code, and I even have the performance metrics and the analysis as code. So what I bring to the table then when I want to reproduce the experiment is the hardware and the auxiliary software, such as the operating system, or maybe TensorFlow or something like that, or some mathematics library. And then I get the graphs, the tables, the figures, everything. So I just have to look at them and see whether I interpret them in the same way as the original authors did. And then I say, it's good. And then I reproduced the experiment. So much less of me in this reproducible experiment than if I'm a psychologist. Then more of you are part of the reproducibility experiment. Okay. So there are two dimensions here that I'm thinking about reproducibility experiments from. So first is the input to the process, the reproducibility experiment, and then it's the output, the conclusion. So which documentation do I have access to? That is one of the dimensions, and this is the type of the reproducibility experiment. Okay, it decides what type of the amount of documentation I have decides the type of reproducibility experiment I can do. And then for the other dimension, which is the conclusion, how is it reached? Okay, this is the degree of the reproducibility. Okay, to which degree am I able to reproduce your experiment? Okay, so first let's start with the degree, and the degree was about conclusion, so the output of this process. And this, if you run a machine learning experiment, you have the outcome. The outcome is, so for an input picture of a cat, I run it through my machine learning algorithm, and I get it to classify this as a cat or a dog. So if I get the exact same classes for the images as you did, then I reproduced it at the outcome level, sort of, because I get the exact same outcome as you did, then it's good. And if that happens, if I get the exact same outcome, I can just reuse your analysis and your interpretation, and I'm good. I got this, I reproduced your experiment. Then I can look at the analysis. So I might still get a different outcome that you. So you have in machine learning experience, deep neural network, they have some uncertainty to them. So I might get some different images classified as dogs and cats than you did, but most of them are. So I can redo the same analysis as you did. I will still get the same result. And then it's good. I can just use your same interpretation, and I reproduced your experiment. Finally, I can even change the analysis. I can use different metrics than you do. And even if I change the metrics, I can still interpret them in the same way. Maybe you say that algorithm A is better than B, and I say, yeah, using my metrics as well, I get the same conclusion. I don't have to change my belief. Your hypothesis was accepted when I did it even. Okay, so these are the sort of degrees of reproducibility. And then we have three different types of documentation. These are the input to the reproducibility experiment. Okay, and we have the text, which is the paper, the research protocol that was written, that I can read. You have the code in a machine learning experiment. You can share all the code that you had. Or we have data, the observations that were made. You can share the data as well. And these are three different types of documentation of your experiment that can be shared when you're doing experimentation on a computer. Which means that we can talk about different types of reproducibility experiments. So I can do the experiment based only on your description on the paper. I can do it based on the text that you had with the code. I can do it with the text that you had with the data, and then I had to write the code myself, but I can still reproduce it. Or I can do everything because you shared not only the text, but also code and data. And this allows us to talk about, okay, so I did this type of reproducibility experiment. It was an R4 because you had shared all your code, all your data, and your paper. And I was able to reproduce this at this degree. I didn't get the same outcome, but I did use the same analysis and draw the same conclusion. So therefore, I did it at the analysis degree of reproducibility. And now I can classify my reproducibility experiment and say that this is what I got from you, and this is to which degree I reproduced the experiment. Oh, I'm quick. That's good. Because I always talk too much. So, which is good because then so this is basically what this paper was about. It was written a year ago or more than that. And I've thought about this image. So we need to be more explicit. Okay. So why did I fail to reproduce the experiment? So what are the sources of irreproducibility? Okay. There are quite a lot of research on the variability. Okay, so in machine learning, we talk about there is some algorithmic variability because, for instance, neural networks, they have some stochastic parameters such as dropout that sort of drops the updating of certain weights in the backpropagation algorithm. And you, of course, have different parts, but you also have a variation that comes from the computer itself. Okay, so it comes from how you initialize your random number generator. So which seed you use to initialize it actually decides the performance of your algorithm. It could actually change the performance with up to 3 percentage points, which means that a result could be sort of state of the art or mediocre only based on which seed you use to initialize your random number generator, which is kind of mind-blowing. What could change your the variability of your results could be which operating system you're running it on. Are you doing parallel computations? That might change sort of floating point operations. They aren't the same if you add them in the same direction because there are some rounding errors there, and this is truncation errors, which means that your computer will change the output. So what is the variance caused by the algorithm? What is the variance caused by the hardware we're running it on? These are two things that sort of started to see people discuss in the community, but there are others as well. And this is a paper that we are writing just now, and we're submitting it in a very short time. So I'm giving you things I haven't really thought perfectly through yet, but I have to do that in a week. So they are fairly convergent on where I am. So you have some things that are the study design factors. How you actually design your study will affect how reproducible it is. For example, the computational budget you have will might change the results. So are you able to run your computer for a week or 2 weeks, 2 months, or 2 years? That might change the result. And then you have the algorithm factors. So if you shuffle data, if you use random initialization of the weights in your neural network, do you use stochastic layers or hyperparameter optimization? Which algorithm are you using? Different hyperparameter optimization algorithms will change your results and might be better or worse results. You have observation factors, data set bias. So if you don't share your data set, but it has a bias, when I'm sampling or getting a new data set, I might not be able to reproduce results because the data sets are different. How did you pre-process your data set? Did you use data augmentation? Was there any data leakage in your study? Did you do stochastic data sampling from this data set that you had in order to update your model? That will also change the result of your algorithm. In reinforcement learning, the way the environment sort of responds to the action by the robot or the agent could be stochastic. And could have the same sort of issues with truncation of floating point errors. So it might be slight differences which might expose sort of the rest of the actions made. And you have evaluation factors. Did you do error estimation? Did you do it properly? Many papers in machine learning don't really do that, so you have no idea about the error of your algorithm. You have selective reporting of results. I test on this, and this data set, but I didn't test on these. And that's because I did fairly poorly on this. But I'm not telling you, I'm just saying that some others, you use this and they did, I did better than them. So I might overclaim the result. I could have used stochastic baselines. And this stochasticity of the baselines, if it's a neural network, it might have the same problems that all of this implementation algorithmic problems. So I might initialize it with a bad seed and it does poorly. And with a good seed, that sort of makes the algorithm much, much better. So it's hard to compare. So did I tune my baseline or my algorithm? I didn't tune the baseline. Then state of the art might actually change because I said this was state of the art algorithm, but I didn't tune it very well. But my own algorithm, I tuned it very well. So it looks like my method is much better, but it's just depending on how much tuning I did of the algorithm. And then there are documentation factors. What is it actually that I document? Do I document all of these boxes to the left? If I don't, well, there might be a variation in how I do my experiment contra how you did it. And did I talk about all the experiment details? Did I give you all the implementation details? Because how I implement my algorithm, if I use arrays or hash tables, it might actually change the performance of my algorithm. So minute details of implementation of an algorithm might actually change the result. Did I actually tell you the exact steps I took, so of the workflow, my scientific workflow? If I didn't, if I changed 2 steps, then that might affect the outcome of the algorithm. Did I share the data? Did I share the code? Published lots of paper on this. And this, very proud of this, is the front page of AI magazine. I wrote a paper called Standing on the Feet of Giants, and the artist made this picture, which I really loved. So thank you very much.
Thank you, Erik. Questions from the hall here?
It was crystal clear.
Yeah, please. Tell us who you are first, remember.
Okay, My name's Richard Higgs. I run a company that